Until quite recently, most people thought of the oceans and atmosphere as separate systems, but they aren't. They interact and influence one another on a wide range of scales. The most dramatic example of the interaction between ocean and atmosphere occurs in the tropical cyclone belt, where typhoons and hurricanes are born. Hurricane Allen in 1980 was the most severe hurricane to hit Jamaica for several decades. Even more damaging was Hurricane Gilbert in 1988. Hurricane-force winds generate heavy seas which batter the shoreline and leave a trail of havoc on land, which is all too plain to see. But even when there are no hurricanes, currents and waves are continually reshaping the coastline. Sea defenses, groins to stop the beaches being carried away, and large boulders to dissipate the energy of the waves, rarely stop coastal erosion completely. But here in the tropics, the coastline is protected by three natural defenses: mangroves, seagrass beds, and coral reefs. Conservation of these three ecosystems helps to conserve land. Anyone looking at this tangle of roots and branches might be forgiven for thinking that mangrove forests are fit only to be reclaimed as building land. But mangroves are vital for the protection of the coastal environment. During storms, they protect the land from waves, and sediment washing off the land is trapped by their roots, building up new land to support yet more mangroves. Mangroves are a remarkable group of trees. The red mangrove is one of the few plants in the world able to grow in salt water at the edge of the sea. Their roots provide a wonderfully protective nursery for young fish. Some mangroves secrete excess salt through their leaves, and aerial roots exchange gases directly with the atmosphere because the waterlogged soil contains little oxygen. Oysters grow at the waterline. They provide a natural source for more intensive cultivation of oysters on strings hanging from floating rafts in sheltered bays. Moving seawards from the mangroves, another remarkable type of plant grows in abundance. Seagrasses in shallow waters use carbon dioxide dissolved in the water and energy from sunlight to grow. Their leaves provide shelter for young fish, and algae growing on them provide food. An extensive root system helps to bind the fine sandy sediment, which accumulates in the sheltered waters behind coral reefs. Coral reefs are the great natural outer defenses for many tropical coastlines.
All these clean white stones are fragments of coral flung up by Hurricane Gilbert in 1988. You might think that that hurricane built this whole rampart, nearly 3 meters high. But if you look down here, you can see blackened stones, partly covered by the new ones, that were flung up here by previous hurricanes. And we can see elsewhere that hurricanes happened in the ancient past as well. This is a fossil coral reef. It's been dated to the late Pleistocene, 110,000 years ago. What's fascinating about it is this layer of tumbled and overturned massive corals, which must have been destroyed by a violent storm. Whereas it may have taken thousands of years for this whole section to be laid down, this much of it was deposited in the space of a few hours over 100,000 years ago.
The living reef consists of a skin of anemone-like cells called polyps, growing on calcium carbonate foundations of their own creation. During the day, the polyps of many species lie low, perhaps to avoid predation. But at night, they extend tiny stinging tentacles to capture passing plankton. The coral animal contains within its tissue a multitude of microscopic single-celled algae, the zooxanthellae, which use the energy of sunlight to photosynthesize new organic matter from the carbon dioxide dissolved in seawater. Much of this primary production is transferred to the host coral, as if the algae were paying rent for their accommodation. In return, the algae receive inorganic nutrients, especially nitrogen and phosphorus, direct from the waste products of coral metabolism. This mutually beneficial relationship is a fine example of symbiosis, and it enables corals to thrive in these nutrient-poor tropical waters. Typically growing at a centimetre or so a year, they gradually build up a complex habitat for many other organisms. An oasis of life.
A coral reef at night is quite different from what it's like during the day. Most of the reef fishes, which depend on light to see and feed, have gone to bed. The coral now have to turn to the serious business of feeding like animals with their tentacles extended. Many of the invertebrates, free of the threat of predation by the fish, have come out. Even tiny planktonic animals come up into the water column.
This is a basket star, an echinoderm related to brittle stars. During the day it was hiding, but now it has emerged to feed on plankton and has spread its many branched arms into this huge collecting fan. The other nice thing about a night dive is that you never know what else you might see. Here at Discovery Bay, Jeremy Woodley has been making a particular study of the reef. Over 2 decades, he has built up a series of photographs showing coral growth, competition, and the effects of natural disasters like Hurricane Allen in 1980. But damage by human activities is becoming a major concern for scientists studying coral reefs all over the world. Here, students from the University of the West Indies are carrying out a reef survey using the chain transect method. They note the species and other details of the organisms directly below each red ribbon. Surveying a reef like this on a regular basis can give an early indication of the effects of pollution. Here, nutrients in urban runoff have caused an explosive growth of bryopsis, a seaweed which has overgrown the living coral, leaving only its bleached dead remains. In time, the protection afforded by the reef will disappear, leading to serious erosion of the shore behind. But nutrients in natural groundwater percolating from the land can sometimes provide a new resource.
There are some 15 species of Gracilaria that occur in Jamaican waters. Here, some 5 species that I've collected in waters just in this bay. They are survivors of Hurricane Gilbert, and part of the reason they survived is because of their thick, gelatinous texture. They're very variable in appearance from one to the other. An interesting thing with these algae, part of their strength with respect to hurricanes, is that they contain agar, a material that's widely used in the food and pharmaceutical industry as a thickening agent. We've been experimenting with cultivating these algae inside of these cages made out of plastic mesh, which we suspend from bamboo rafts in shallow water here in Discovery Bay behind the reef. One unusual feature of these waters is that they contain freshwater springs in the back reef. And these springs are driven by groundwater that's soaked into the interior of Jamaica and flown underground and reappears as cold, buoyant plumes, which you can see here when we've injected a yellow dye into it. As you see, the water rises right up to the surface, carrying with it very high levels of nitrate, a nutrient that's in critical short supply in most reef environments. We've found that these algae will grow 3 to 5 times faster in spring waters than they will outside of them. And as a result, these particular environments have a tremendous potential for the cultivation of these algae on a commercial basis by fishermen.
Whilst natural enrichment of the seas in Discovery Bay may be beneficial, the story of damage by pollution in the heavily populated south is all too common.
Kingston Harbour is one of the largest natural harbours in the world and is bounded by a city of nearly 1 million people. Almost all of the sewage wastes and other wastes from that city are discharged into the harbour. And the project which we are undertaking here is aimed at studying the effect that the discharge of those wastes into the harbour and then out of the harbour into the open sea here along the Hellshire coast is having on this coastline. The project is being undertaken by a multidisciplinary team of marine scientists from the University of the West Indies. And we are looking firstly at problems of water chemistry, particularly the concentration of nutrients such as nitrates and phosphates, and the effects that these have on the environment. We are looking at sediments, and in particular, the existence of trace heavy metals in the sediments, which are themselves an indication of pollution. We are looking at the dynamics of water motion and the way in which the water is exchanged between the open sea here and the harbour. We are looking at the problems of reef decay as a result of pollution and the way in which coral is dying back and large amounts of seaweeds are growing on top of the old reef. And all of this gives rise to changes in water motion which cause changes in the deposition of sediments on the beaches and in the erosion of beaches. The sort of work which we have been undertaking here on the Hellshire coastline is providing us with a scientific database which we can use to advise governments and other agencies throughout the Caribbean.
To understand the marine environment anywhere, not just in tropical coastal waters, oceanographers must have a multidisciplinary approach. But it wasn't always so.
Way back in the past, when the Challenger first set sail more than 100 years ago, the scientists who were participating on that cruise were biologists and physicists, and the biologists did biology and the physicists did physics. Now, the modern oceanographer has to be able to have some sort of knowledge of physics and chemistry and biology. And you can see this sort of problem when you look at the sorts of difficulties that the people who study the deep sediments get into. Here they are looking at the past record that is preserved in the sediments, and they have to unscramble this sort of garbled message that the biology has put as the material sank through the water column, that the physics has inflicted by stirring up the sediments before they've settled on the seabed, and by the microbial degradation of the material actually in the sediments. So the modern oceanographer today has to know an awful lot about the sort of things that the physicists study, the chemists study, even if he's a mere biologist like I am.
Scientists have been investigating the biology of the deep sea floor for well over 100 years. Yet this environment can still provide considerable surprises. Most dramatic in recent years is the discovery of the rich and unique fauna associated with hydrothermal vents on the mid-oceanic ridges. Equally surprising has been the discovery of a strong link between events in the surface layers of the open ocean and the deep sea floor.
Until well into the 1970s, the prevailing view of these deep areas of the ocean was of a dark, still, food-poor environment, quite untouched by the perturbations affecting the layers above it. Animals living in these depths were dependent for their existence ultimately upon the organic matter produced in the sunlit surface zones where photosynthesis can take place. The input of organic matter to the deep sea was assumed to arrive at depth mainly as a very fine rain of tiny particles, a few microns to a few millimeters across. These particles, dead and dying algal cells, the bodies of small planktonic animals and their fecal pellets, were assumed to sink slowly through the water column, being recycled by midwater organisms in the intermediate layers and taking weeks, months, or even years to reach the deep sea floor. By the time they did so, any seasonality in their origin was assumed to have long since disappeared, so that the supply of food to the deep sea floor was thought to be evenly distributed both in time and in space. Then, in the late 1970s, these ideas started to be challenged. Sediment traps set in mid-ocean, 2,000 or 3,000 meters beneath the surface, but still well above the bottom, were found to collect very variable amounts of sedimenting material. These variations seem to be correlated with similar variations in the plankton productivity in the surface layers. But 2 or 3 years later, the first direct evidence of the seasonal deposition of phytodetrital material actually on the deep sea floor came as a bolt from the blue to iOS biologists looking at quite different phenomena. Since 1977, a group of us had been studying the benthic biology of the porcupine sea bite, a sort of horseshoe-shaped depression in the continental slope to the southwest of Ireland, opening out onto the porcupine abyssal plain at a depth of about 4,000 meters. During this study, routinely we used an epibenthic sledge, a metal frame with nets attached to the back of it, which is dragged across the seafloor to collect animals living on and within the sediment. Now, because we didn't expect seasonality to be an important factor at the depths that we were working, it didn't seem to matter very much when we obtained our samples. Consequently, by chance, our early cruises were all in the winter months of the year, between about October and April. During this time, we obtained some thousands of photographs of the seafloor, and they all seemed to confirm the old idea of the deep sea floor as being a monotonous zone where nothing very dramatic ever happened. Typically, they showed a muddy bottom, often marked by tracks and trails of benthic organisms, and quite often we saw pictures of these benthic beasts walking across the seafloor ahead of the net. Then, in 1981 and 1982, we had cruises at a quite different time of the year, in May and July. The photographs obtained this time were quite different. The seafloor was just the same, with bumps, mounds, and depressions, but now when we look carefully, many of these depressions were filled with a curious, dark-coloured, amorphous, nondescript, fluffy sort of gunge. Often this gunge was so abundant as to make these photographs appear to be out of focus, and there might even be enough of it to hide quite big organisms. For instance, here there's a brittle star sitting in a depression on the seafloor. The brittle star is about 20 centimeters across, but all you can see are the tips of its arms sticking up through this dark-coloured, fluffy material. What on earth was this material, and where did it come from? Clearly, in the period April-May, something very curious was happening on the deep sea floor. But what?
This suggestion that the appearance of the deep sea bed may change seasonally ran quite contrary to what we then believed. One obvious way to examine this further was to photograph in time-lapse one patch of seabed over a long period of time. This is the equipment we use to do this. This is a deep sea camera which photographs a patch of seabed such as this. Of course, there's no light down there, so the area is illuminated by the flashlight. In order to get the rig down to the bottom and to hold it there, we use this massive iron tripod here. And when we want to bring the equipment back up to the seabed, this ballast weight is left behind after the trigger here is activated from the research ship several kilometers above. The buoyancy spheres then drag it back up to the surface where it's recovered. So much for the technology. What did we actually find out? In May 1983, we dropped this rig into 4,000 meters of water on the abyssal plain just next to the United Kingdom. We set the camera to photograph every 8 hours and left it on the seabed in this rather hostile environment until our return several months later. We're looking at 2 square meters of seabed, And to give a feeling of scale, the mound on the right is about 18 centimeters across. As you can see, there is little change in the appearance of the seabed during May and most of June. Some animal tracks are formed, particularly at the bottom of the frame, while others degrade, but the scene is largely unchanged. In the latter part of June, however, you can see dark blobs of material of up to a centimetre in diameter arriving on the seabed. These move about and change in appearance, but by mid-July, the seabed is covered with a thick layer of detritus. Unfortunately, the film ran out in mid-August, so we do not see a complete return to the winter situation. So what, you may ask, is the relevance of these observations to the oceanic environment as a whole? What we've demonstrated is that although the top and bottom of the ocean are separated by several kilometers, there is in fact a very close coupling between these two environments. Processes occurring in the top 50 meters have a direct and large effect on the rest of the water column beneath it. This deduction was only possible when we were able to determine that the fluffy detrital layer was fresh phytoplankton with an oceanic species composition. In order to do that, we had to collect undisturbed samples of the sediment using a novel sampling device.
Well, this is the moment of decision. Has the crepe corer taken an undisturbed sample of the seabed? And here you see we have a fine plug of sediment with the surface of the sediment quite undisturbed and with no sign of material being wafted up into suspension into the overlying water, which is quite crystal clear. Now, a corer of this type is very good for taking samples in inshore waters, but it isn't rugged enough and it doesn't take enough core samples for use in the deep sea. And for this we developed a multiple corer which is much larger and heavier and capable of taking up to 12 core samples at a time.
The corer can go down and back through 3 kilometers of water, a round trip of 6 kilometers, in less than an hour. Each of the plastic core tubes has collected a core of undisturbed sediment. Most of the time, the top of the core looks like an ordinary white mud. But sometimes the core brings up a soft, flocculent layer of greenish seasonal debris, the phytodetritus, which lies like fluff on the surface. Under the microscope, the phytodetritus consists of a loose matrix containing remains of single-celled planktonic plants and animals that live in sunlit surface waters. Most of these organisms are smaller than the thickness of a human hair. All this fluff provides a food bonanza for organisms living on the sea bed. And when we look closely at the animals living down here, 4 kilometers deep, the green color inside their transparent bodies shows that they have been feeding on plant debris, on phytodetritus, which can only have come from the surface waters above.
The discovery of large amounts of phytodetritus on the deep sea floor is obviously a very recent one, but it's just possible that this material was noticed more than 100 years ago. In the summer of 1857, a Royal Naval Survey vessel carried out a number of soundings across the North Atlantic in preparation for laying the proposed transatlantic telegraph cable. Now, these soundings were obtained with a simple piece of equipment which took a tiny sample of the seafloor each time a sounding was obtained. These samples were given to the eminent Victorian scientist Thomas Henry Huxley, and when he first reported on them, they appeared to be quite typical of deep-sea sediments, dominated by foraminiferan shells and coccoliths. 10 years later, however, Huxley re-examined these samples, and at the annual meeting of the British Association in 1868, he made an astounding announcement. The forams and coccoliths, he said, were embedded in a glutinous matrix, which he was convinced was the living protoplasm of the simplest organism so far discovered, and he named it Bathybius. Marine scientists all over the world became very excited at this, for surely this reticulum of protoplasm represented life being spontaneously generated all over the deep sea floor, fitted in very nicely with Darwin's theory of evolution, which had come to them only a few years before. So people started to look for it. And in the 2 or 3 years after Huxley's original announcement, several reports of Bathybius came from a variety of localities. It was quite natural, therefore, that at the end of 1872, as the Challenger was preparing to sail on its epic 3.5-year voyage around the world, the scientists involved had the further elucidation of the Bathybius story as one of their top priorities. But throughout the cruise, despite careful scrutiny of each benthic sample as it came aboard, no sign of Bathybius could be found. Finally, in 1875, as the ship approached Japan, the expedition's chemist looked at some deep-sea sediment samples that had been preserved for some time, and he noticed that in those samples that had been preserved in alcohol, there was a glutinous, transparent precipitate. He looked into this a little further, and after a few tests, he came to the conclusion that Bathybius was nothing more nor less than calcium sulfate, which had been precipitated out of the seawater in the samples by the alcohol used to preserve them. The news was sent back to England. Huxley accepted this explanation and admitted his gross error. And that was more or less the end of the Bathybius story, except as an example of the type of error that even the most eminent and revered scientist could make if he wasn't very careful. But the samples that Huxley had based his original description on, and also those positive records of Bathybius in the next 2 or 3 years, were all taken in localities and at times of the year when we now know phytodetritus is to be expected on the deep sea floor. Whereas the Challenger negative samples were either taken with gears that you wouldn't expect to collect phytodetritus, or in places and at times when you wouldn't expect phytodetritus to be there. So it's just possible still that Huxley's Bathybius was actually phytodetritus. Indeed, when you look at his original descriptions, they fit phytodetritus to a T. An irregular network of matter resembling white of egg, he says, enclosing small bodies in the shape somewhat like oval shirt studs, the coccoliths. And if you compare the original illustrations of Bathybius with modern electron microscope photographs, they're amazingly similar. Huxley was clearly totally wrong in interpreting this material as the protoplasm of the simplest organism that had ever been described. But perhaps he was not quite as stupid as his contemporary and subsequent critics have accused him of being. Perhaps more recent oceanographers are more open to criticism for not realizing and recognizing the significance of such an important phenomenon for more than 100 years.
Until the Second World War, offshore navigation was very much sextant and compass. This was very good, but the Second World War gave us the impetus to go on to electronic position fixing. The first of these to come out was the radar, an example of which we have here. And of course we saw the first electronic navigational aids, such as Decca, which we have in the corner, and the Loran system. Now, of course, we've moved on to satellite navigational systems, the earlier version of which was very accurate, but time-wise, it was half an hour to an hour between fixes. The modern version, it's hoped, is going to give us continual positions anywhere on the globe with an accuracy up to about 20 meters. But of course, with oceanographic research, we're interested in more than just position data. We're interested in bathymetry. And this is where the echo sounder comes in. We have a modern echo sounder on board, which gives us the bathymetry in color, a color enhancement, which helps us very much to see the detail on the bottom. Oceanography demands not just accurate position fixing, for example, recovering current meter moorings after periods of up to a year, but also maintaining constant speeds and courses when towing monitoring and sampling devices, often several hours in adverse wind and current conditions. On the other hand, when we're doing a CTD, we're required to keep station for several hours while the instrument descends to several kilometers. We have to maintain a vertical wire angle for this. When we're towing bottom sampling devices such as epibenthic sledges, trawls, camera gear and so on, we need to keep to predetermined tracks. Each scientific demand is different, often asking the impossible, but we try to please.
Nowadays, the oceans aren't investigated only from ships. This is a Nimrod of the Royal Air Force on a routine surveillance flight over the North Atlantic off Scotland.
Steve, on into what radar assessors we use. Could check that all on 4 correction.
In the maritime job, we constantly need to update the sea state and the wind velocity. We do that purely visually. Today, for example, we're looking at the amount of streaking over the sea and the amount of white water. We have today black streaks on the water, which indicate the wind is roughly 18 to 20 knots. If it was white streaks, we'd be talking over 20 knots. Together with that, we're looking at the amount of white water that there is. And today, there is an amount of white water. The waves are breaking over, which again indicates sea state 3 to 4.
Okay, Rockall's coming down in about half a mile.
We're flying east of the Rockall at 300 feet and 200 knots. The wind velocity today, looking visually, is 240, 18 knots, sea state 3 to 4.
The Admiralty research vessel Newton is also in the Rockall area. Oceanographers aboard the Newton are looking at the way currents and the distribution of temperature and biological productivity are influenced by the topography of the Rockall Bank. One of their instruments is an underwater glider called Seesaw. It follows an undulating path as it's towed behind the ship, recording temperature, salinity, chlorophyll concentrations, and other oceanographic properties. But if all you need is a temperature profile in one location, you can use an expendable bathy thermograph, XBT for short. As the weighted temperature sensor sinks to the bottom, it sends information by wire up to the ship. Back on the Nimrod, the crew prepare to drop a rather more sophisticated aerial XBT.
Okay, crew from TechNav standby, Bathy channel 16, in position 5728 north, 1256 west. Channel 16, now, boys gone.
On contact with the sea, the XBT splits in two. The temperature sensor sinks, leaving the transmitter floating on the surface at the end of the wire. And on board the aircraft, the change of temperature with depth is displayed on the screen. Direct observations and measurements from ships and aircraft provide local sea truth data. But to get a global view, we have to go a lot higher. Satellites have become more and more important in oceanography since the late 1970s. This is ERS-1, the first European remote sensing satellite, in a polar orbit at almost 800 kilometers altitude. Its sensors can measure sea level to centimeter accuracy and temperature to a few tenths of a degree, data vital to WOCE, the World Ocean Circulation Experiment. Satellites are routinely used in day-to-day weather forecasting. But prediction also requires sophisticated modeling with powerful computers.
The ocean has weather and climate too, but they're much more difficult to predict because ocean features are so much smaller than the atmospheres. For example, atmospheric cyclone might be 2,000 kilometers across, while an ocean eddy is only 30 kilometers across, and the ocean is full of eddies. Similarly, atmospheric features can persist for a few days, whereas ocean features can last for years. Now, if you look at the world's oceans, you'll see they're nearly always bounded to east and west by land. Just like the coffee is held in this cup by its edges. Now, if I blow over the coffee, it's like the wind blowing over the ocean. If the cup didn't have any edges, then the coffee would simply move faster and faster in the direction of the wind and build up momentum forever. But because the cup does have two edges, the depth of the coffee can build up on the far side of the cup. And this makes a kind of backwards pressure gradient, which helps hold the coffee in the cup so it doesn't pour over the edge into my lap. If I stop blowing, then the pressure gradient can relax and the coffee slumps back to its previous position. We can see this in data from the Pacific Ocean. When the trade winds collapse, then the water piled up against the coast surges back across the Pacific. But there is just one ocean where these simple ideas won't work. In the Southern Ocean, the wind blows roughly eastwards around the Antarctic continent. Now, there's a band of latitudes between South America and Antarctica where there is no land anywhere around the globe. In this band runs the Antarctic Circumpolar Current, the largest ocean current in the world. Now, our simple coffee cup model would predict that the Antarctic Circumpolar Current would flow ever faster and faster, eastwards and eastwards, gaining momentum all the time. This obviously doesn't happen, but it does happen in all the simple models we have of the Antarctic. To explain what really happens, we modelers find that we have to include pretty much all the physics we think take place in the real ocean and put it all into a state-of-the-art computer model running here at the Rutherford Laboratory. This is a bird's eye view of Antarctica. The black parts are land. Here's the tip of South America. Here's Antarctica. What is shown here is the depth average flow of the ocean. The bands of colour represent the amount of water flowing round. Now, we modelers find it easier to think of this in terms of a Mercator projection. So let's open the map out. Now, it's somewhat easier to recognize South America now. This black strip along the bottom is the unwrapped coast of Antarctica, and the circumpolar current is running from west to east here. Now, this region off South Africa is particularly interesting. Let's look at it in more detail. The Agulhas current runs down the side of South Africa. When it runs out of land to hug, it breaks off into these deep eddies which spill off one by one into the South Atlantic. Over time, these eddies develop. Well, we're quite pleased with this model. But is our model any good? How do we tell? The only way is to test your model against reality. If the model and reality look similar, then we can believe that we're beginning to get some of the physics correct. In our example here, the model developed eddies, especially over ocean seamounts, which is the kind of thing that's observed in reality, and it gives us confidence. On the other hand, the model represents the floor of the ocean rather like a collection of children's building blocks stacked up on top of each other. And it's hard to see how water can flow really smoothly over a jagged surface like this. So there's always scope for improvement in the physics. Now, modeling isn't just about getting the right answers, though. What we want to do is weather forecasting for the oceans to predict things before they happen. If a fisherman wants to go out fishing, he needs to know where the nutrient-rich waters will be tomorrow. The Thames Barrage is very expensive to raise and lower. But if it's raised in an emergency, it'll be because a model predicted a storm surge rushing up the Thames to flood London. It's no good predicting things after the event. And that's why we need this vast computer behind me. It's not that the mathematics are unbelievably hard, it's just that we have to do so many sums in order to run the model. The model stores values of temperature, salt, and water movement on a three-dimensional grid of points and updates the values every so often. Now, it's very important but you don't have points too far apart, else an eddy could slip between them. It's also important that you update the model fairly often, otherwise you get the wagon wheel effect. We've all seen Western movies on television in which the wagon wheel appears to go the wrong way round. What actually happens, of course, is that between two frames of the television, the spokes of the wagon wheel move nearly one notch, and this makes it look to our eyes as if the wagon wheel moves slowly backwards. One of the first models I ever ran here looked to us as if the waves were going the wrong way round, so even experts can get it wrong. So we end up with a lot of numbers. Our Antarctic model has over 20 million values to be updated every 30 seconds. If you had a calculator like this, you could run our model. It's just that it would take you over 65 years to update the model by just 1 hour. So, if our models don't quite look like reality yet, it's not just the lack of computing power that's the problem, although we always need more. It's that we're probably neglecting some important physical factor that's out there in the real world. And for that, we need physical models.
In rotating tanks like this one, hundreds of kilometers are represented by tens of centimeters, and a day's rotation of the Earth is over in a matter of seconds. Here, the circular ring represents a coastline, and the red fluid represents less dense river water flowing into the ocean. But it doesn't flow straight out. It's constrained to flow along the coast by the Earth's rotation. This is the view from the camera fixed to the rotating tank. Wave-like lobes develop along the unstable boundary between the incoming freshwater and the surrounding seawater. Similar wave-like patterns can be seen on satellite images of coastal waters. Here, processes within the body of the ocean are being investigated. Looking through the side of the tank, we can see an initially well-mixed turbulent fluid. As the model ocean continues to rotate, long vertical columns develop. These could be simulating eddies extending down into the deep sea.
But no matter how successful we are at modelling bits of the oceanic system, the real world is far more complex. It's an interactive mixture of geology, physics, biology and chemistry, and you can't study one of these aspects without taking the others into consideration. For this reason, oceanographers have to develop a wide range of instruments to measure all sorts of parameters. But the ocean's a very hostile environment and seawater's a very corrosive fluid. Often what we put in doesn't come back at all, and when it does come back, it sometimes doesn't look the way it did when we deployed it. These are the remains, for instance, of a mooring that was deployed to the southwest of Ireland in 1983 on an acoustic release system. When we went back a year later, it refused to respond to our signals and didn't come up, so we thought we'd lost it for good. And by chance, in 1989, 6 years after it was originally deployed, a French expedition came across it floating at the surface of the sea about 100 miles from where it was deployed. And as you can see, this current meter, which looked like that when it was first put in, is now pretty well battered. And part of the same rig was a camera with its lens here and light-tight case. The light-tight case was still in position, and the film was inside here, but unfortunately it was completely ruined. So the ocean won again.
For many years, oceanographers have been using all kinds of towed instruments to gather their data from the ocean floor. For example, we use Gloria to map the seabed. And we also use Seesaw to make measurements of the physical and chemical properties of the water masses. The problem is these things are tied to a ship, and that means we can only go as slowly as the ship does, and we're subject to all the limitations of weather and so on. So the trick for the next decade is to be able to take these things off the leash and let them roam around in the ocean making the measurements for us. One is called Doggy. It's actually a free-ranging Gloria. And the idea is that we let it off the leash and it will roam around flying just above the seabed, taking high-resolution measurements of the geology and geophysics of the sea floor. Perhaps an even more interesting one is our Dolphin instrument. Now, dolphin is like a free-ranging seesaw. It's going to move up and down through the full depth of the water column, along long tracks through the ocean, making physical and chemical measurements. The neat thing about dolphin is it's supposed to come to the surface every now and then and telemeter its information back to base via satellite so that we can see what's going on and monitor progress. One of the interesting things about the dolphin concept is it'll actually allow us for the first time to go under the Arctic ice and take lots of oceanographic measurements. And as you can appreciate, this is a very difficult thing to do at the moment with the technologies that we have.
Automated underwater vehicles are all very well, but it will be some time before such vehicles are capable of stopping in their tracks when they come upon scenes like this. Voracious amphipod crustaceans tearing bits off a living siphonophore, an animal related to the Portuguese man of war. Other wonders of the deep oceans are animals like these, so delicate they were never observed before the development of manned submersibles in the 1970s. They would be instantly destroyed by any conventional collecting gear. The significance of these amazing creatures has been recognized just in the last couple of decades, and their enormous diversity has become apparent only since the 1980s. Submersibles and underwater cameras have shown us that there's life at all depths of the oceans. Deep-sea benthic animals like this, with long trailing tentacles, show that even down here, kilometers deep, there are currents too. Throughout the oceans, these deep currents waft the scent of prey and corpses downstream, and the predators and scavengers quickly gather round.
Even the most robust animals that withstand the capturing process lose much of their beauty and most of their charm when they finish up in preserved collections like these. Nevertheless, such collections are terribly important when we want to compare the situation now with what it was 10, 50 or 100 years ago. And this problem will be even more significant in the future when, as we know, in the next 50 or 100 years, there'll have been major changes to the world climate, and we must make sure that we leave a legacy of standard samples for future oceanographers to compare their situation with the situation today. But far more important than the collections, we must ensure that the environment itself is not severely damaged, so that those future oceanographers can revisit the places in the ocean that we've been to and can see these beasts in their vital living state and will not be restricted to looking at preserved, dead, lifeless specimens like these.